In the previous lessons, we learned how to write electron configuration using the periodic table. And just a quick review, we know that this period number right here represents the energy level. So let's choose an element for this example. Let's choose oxygen, how about that? And then if we look at the periodic table, this entire group right here, including the helium, they are S sublevel. Then go over here, we would have the P sublevel. And lastly, we have the D sublevel. But for the D, we start with 3 and then 4. So D is 1 less than the S, okay? And now if we go back and look at oxygen, the oxygen electron configuration would be start with 1 and 1s2 because they are the same sublevel. Go down, we would have 2s2 go across. Now we move on to the P sublevel, we would have 2p1, 2, 3, 4 because we stop right there. So 2p4. Now today we are going to look at the experimental data that support the existence of sublevel, energy level, and the electron configuration. The experimental data that we are looking at is called Electron Spectra, or PES, which show the relative numbers of electrons ejected from an atom at particular binding energies. So here you have your relative number, okay? And in this case, we have the binding energies. So the PES are experimental data that support shells and subshell and electron configuration of atoms. In this case, let's look at this more closely. We notice that at 125, and the unit for binding energy is megajoule per mole. And in this case, at this particular peak right here, we have 125 megajoule per mole. And going down here, we have this peak right here where it's indicate 9.05 megajoule. And notice how this peak and that peak has the same height. And that's why the term relative come into play. That means this peak and this peak have the same number of electrons. And we know that the closer the electron to the nucleus, it will require more energy. And with that information, the electron that is closest to a nucleus would have the highest binding energy, which in this case we know that it is 1s2. And notice how we have 1s2, the next one is also 2s2. And look at the number of electrons, it is the same, so they have the same height as well. Then we know based on the electron configuration, what's after 2s2? We would have 2p6. In this case, this would be 3 times the height of the s, which is exactly right. 1, 2, 3. So that's 3 times. So we have 2p6. Then now what's after 2p6 on your periodic table? We would know that if we go back on the periodic table, and after 2p6, what do we have? We would have 3s2, okay? So we go back now, this right here would be 3s2, which makes sense because if this have the same height as that one, that means the relative number of electrons must be the same. So we have 3s2. And that will be the electron configuration from this PES data. So the first question that we can ask is, write an electron configuration for the PES data above, which we just did. Starting from the very beginning, we have 1s2, 2s2, 2p6 for that one right there, and then we have 3s2, and that's it. Identify the element based on the PBS data above. Well, this would be the last electron right there. That would be the last electron. In this case, which element would have that last electron at 3s2? So go back and look at our periodic table. In this case, the element with 3s2 would be, here we have 3, and here's the s sublevel, this is 3s1 and 3s2. So that would be magnesium. So the element in this case, it is Mg, magnesium. Which peak represents the 2s sublevel? That's easy. We go up here, we look at this. This must be 1s2 and this must be 2s2. So it will be at the peak of 9.05 megajoule per mole. Okay? And then an electron from which peak would have the greatest velocity after ejection? We know that the one that's farther away from the nucleus will require less energy. So the leftover energy will be converted to kinetic energy, which is the energy of motion. So this basically asks which one would be the last electron. In this case, the last electron would be at 3s2. So in this case, it would be the electron at 0.70. megajoule per mole. And lastly, then we have how many valence electron does this atom have? And the valence electron are basically the outermost electron. And the outermost electron are found in the highest energy level, which in this case, the highest energy level is 3. And there's only one 3 sublevel, which is 3s2. So the total number of valence electron would be 2 valence electron. If an atom above form an ions, how would the following variables compare to the PBS above? Well, if these atoms are here, it is Mg, and we know Mg is in group what? In group 2a. And all the element in group 2a will form a what? And all the element in group 2a would lose 2 electrons to become stable. So if it's losing 2 electrons, that tells you that this peak right here will be gone. So you lose 2 electrons. So the answer would be 1 less peak. What about the height of the peaks? Well, remember, this is a relative number of electrons. So the height for the S sublevel will be the same, and the height for the P will be the same. So in this case, the height would be the same. And before we move on to the next question, we need to realize that, again, the D sublevel electron are nearer than the S sublevel, especially when we talk about 3D and 4s. The energy level is lower. So the D electron would require more energy, okay, than the S sublevel, because the binding energy is a lot higher. Where, for example, in this case, the 3D1 would have high energy or require higher binding energy than the 4s2, because the 4s2 is farther away comparing to the 3D1. Likewise, it requires less energy to remove electron from a neutral atom than to remove electron from a positive charge ions, because the positive charge ions right here, okay, if it's losing electron already, the greater attraction of the nuclear force inside an atom will have a greater attraction on the remaining electron. Therefore, it requires more energy to remove those electrons. And likewise, it requires more energy to remove an electron from a very electronegative elements. Because electronegative elements like fluorine, chlorine, they want to gain electron to be stable. So they're not going to give up the electron easily. So these are the two information that they may use to make the question more challenging for you. Now let's look at another type of question for PES, but not in terms of the graph form, but let's look in terms of data form. So I have my binding energy list from smallest to largest, and I have my relative number of electrons. So I don't have a graph, but I have a data table. And the one thing we always look at is this. Always look at the largest binding energy. So this would be the highest binding energy. And why do we look for the highest one? Because that one would be your 1s, okay? Because that's the one is the nearest to the nucleus. So here I would have 1s2, and going next, I would have 2s2, and then I would have 2p6. Then we have 3s2. Then we have 3p4. So the electron configuration is pretty easy. 1s2, 2s2, 2p6, 3s2, and 3p4. And which element has this PES data? So which we're looking for is the last electron, 3p4. So 3p4, in this case, this is our 3 right here, and p is right there. So let's go over here. 1, 2, 3, 4. So it must be sulfur. So therefore, that's the answer. And which binding energy represents the 2s subshell, which is easy, at 9 megajoule per mole. There you go. Then an electron from which binding energy would have the greatest velocity after ejection? This is talking about the last electron, okay? The last electron, which is the furthest away. In this case, it's what? It's going to be at 0.45. In this case, it's going to be at 0.45. And how many valence electrons does this atom have? So again, the valence electron are the outermost electron with the highest energy level. So in this case, we have 3s2 and 3p4. Give us a total of 2 plus 4, give us 6 valence electron. Then again, if the atom formed in ions, how would the following variables compare to the PVS of its neutral atom? So in this case, we know the atom is what? The atom is sulfur, and sulfur is going to gain 2 electrons to form a stable ion with a charge of 2-. So in this case, if it's gaining 2 electrons, the number peak, of course, would be the same because we're not adding any subshell or any energy level. So the same number peak. What about the height of the peaks? Well, at the last peak, where 3p4 now would become 3p6. So it would be higher. And that is how you answer a question about PES using a data table.